Okay, so we're gonna go off of our combined loading problem example on that video, and and so now we have the state of stress, and we're gonna use Mohr circle to use stress transformation. And so we're given essentially every stress transformations problem starts with a given state of stress without a coordinate system. Okay, so that's something we have to define specifically for stress transformation, and that coordinate system is local to that element. And we want to find, let's say for here, we could find either at a new orientation some angle, or we want to find principal stresses, okay, and draw the RVE in this case, or draw and then principal stress state. Let me put that principal stress state, or and in plane, and this would be like another part or another problem, in plane shear stress, max in plane shear stress, max in plane shear stress state, and you want to be able to draw the RVE. And so we'll do this using Mohr circle right here. You can always use the stress transformation equations, but so here we're given the state of stress, and the first thing that we want to do is well, the first thing is here, let me draw it down here. The first thing we want to do is define a coordinate system on the RVE, or on the state on this RVE, okay, or the on the RVE that's given, on given RVE, okay, the representative volume element. And so in this case here, I have here this going on like that. Right here, I have a stress like this. I'm just drawing my RVE out right now. Here, this is 5.855 KSI. The shear stress was 4.79. Let's just use 4.8 KSI and 5.9. 5.9 KSI. Actually, let's just use 6 KSI, so we don't have to get. Yeah, yeah. Let's use 4. Let's keep 4.8 because I'm not. Oh no, we went from 4. Oh, let's just do one. Gosh. Who cares? It's okay. It's okay if I just use 5 and 6. So 5 KSI and 6 KSI to make our computations. Like just because this is an example, right here, and then we'll have 6 here, and then here again, like this. Okay. And so we want to define our coordinate system, our x and y, using a right-hand rule local for this point on the structure. So here, it's typical to choose this as plus x and this as plus y. Okay, that's very typical. And once you define that coordinate system, that means you have established what sigma x, sigma y, and tau xy are now. Okay, and sigma x in this case would be minus 6 KSI, sigma y would be 0, and tau xy would be, I am on the plus x face in the plus y direction, so this would be a plus 5 KSI. Okay, right there. Right. And this is very important. It's almost like equilibrium, almost as important, especially for stress transformation. This is very important. If you can't do this, you're going to get everything wrong. So we have defined the coordinate system. Now we're ready to draw more circles. So that'll be 2. Draw the circle. And really the first thing we're going to draw for Mohr circle is the center of the circle. Center, or we want to locate the center of circle. Okay, the circle center. And so here the center is defined as sigma average comma 0, which in this case the location of the center is sigma average, which is minus 6 plus 0 divided by 2 comma 0. Okay, so these are the coordinates on my axes for Mohr circle. It's going to be minus 3 comma 0 is my coordinate for the center of the circle. So if I'll scroll down a little bit right here. So on this side right here, I'll draw it. Let me put now when I draw Mohr circle, just as I was telling you, I don't like to draw the vertical axis in right away just because I don't know how large that radius is going to be, and I want to try to I don't want to throw myself off in a like a crunch situation, especially like in an exam. So I just draw one axis. I know that this is my plus sigma axis, and then I will call this point right here my center, and I call that minus 3 comma 0. So that'll be my center there. Okay. Then I need the first point of the circle. The first point of the circle is point A, which is really what's given in the problem. And that point is just point A, or the first point that you need is A is sigma x comma tau xy, which in this case is just minus 6 comma 5. Okay, minus 6 comma 5. And the other thing you have to remember is that the plus tau is in the downward direction. Okay, plus tau is in the downward direction. So really, this should be a little bit longer right here. So I go, let me see, let's go 1, 2, 3. There's my minus 6, if you will. 4, 5, 6, negative, and then 1, 2, 3, 4, 5. Right about here, this is my plus tau direction. Okay? Remember, plus tau is downwards. Okay? Plus tau, the plus tau axis, which is going to be somewhere over 1, 2, 3. So right about here is plus tau is this way right here, my plus here. And this point right here in blue represents that first coordinate that I need to draw, which is minus 6 comma 5. And this point right here represents essentially, right here, this represents theta equals 0 degrees. This represents this x being right here, theta equals 0 degrees. Okay? It represents this face right here. It represents this face. This face right there. Okay? That point. On Mohr's circle, this point represents that face. Theta equals 0. Now I have, bam, that's great. I can draw a line connecting my two. And, whoa, that was off. Edit, undo that one. So here, I'll just draw it here. Like this. Right there. Okay, I have that right. And now I want to calculate that radius distance, r. So 2r. And I can do this by, I don't need to get all sophisticated and fancy to calculate r. All I need is that I know that here's a. So here's A, going straight down right here. This distance right here is 3. This distance, oops, I don't need that right now. Okay, it's 3. And this distance is 5. Okay, and so R, the radius, is the square root of, notice all these are in units of KSI, if you didn't know that right now, okay? All these are in KSI units here. But R is just square root of 5 squared plus 3 squared. 5 squared plus 3 squared. Which is 25 plus 9. What is that? Huh? 25 plus 9 is 34. Yeah, what's the square root of 34? Okay? Okay. I think it's less than 6. Should be 5 point something. Let's see. 5.83 KSI, like that, okay? 5.83 KSI right there. So that's what that radius is. The other thing that's important for me is this angle right here because, okay, so the first thing we're going to look for are principal stresses. Is this angle right here, okay? And really what we know from Mohr's circle is that you know, this location, when I swing this arm down right here, this represents sigma 2, my least positive principal stress. And then here, where's my sigma 1 going to be? It's going to be 5.83 So here this is 3, and then 5.83 beyond this negative 3 is 2.83. So right about 1, 2, 3, right about here is sigma 1. Okay, sigma 1 is my most positive principal stress. And remember, this distance right here is just r right here. So that means this coordinate right here is going to be 5.83 minus 3. So this location is 2.83 comma 0 KSI. So sigma 1 is that. And then here, this, my least positive, is here going this way, minus 3. So this number right here is minus 8.83 comma 0 right here. That coordinate right there. So that means that my minor principal stress is negative 8.83 KSI. Okay. And so that's great. I just found like my principal stresses without really, so for principal stresses, and here the principal stresses, and obviously the shear stresses are 0 in this principal stress state, and sigma 1 is 2.83 KSI, and sigma 2 is minus 8.83 KSI. Yay. Okay. And now, because I want to draw that representative volume element, I need to know some angles of how far I need to go. So here, the angle to get to theta, the second theta P2, right here, I'll call that theta P2, is just, again, by simple geometry, that angle is just tangent, inverse tangent, or theta P2 is equal to tangent inverse of the opposite over the adjacent. 5 over, we said 3. Oh, great. Okay. And can someone calculate that for me quickly? Tangent inverse. 50. Oh, whoa, my bad. I got to put that 2 here. That 2 theta P2 is 59 point what? 4 degrees. All right, so about 59 degrees. Very good, right? And then so that makes theta P2 29.5 degrees about, okay? About 29.52, okay? But anyway, 29.5 degrees, whatever. It's about the same. 30 degrees. So here, that is, that's great, okay? And so the thing you have to remember is that, okay, that's great. And then I go theta P1 is just really the, the opposite of this right here, this way, 180 minus 59.04, or, 90 degrees from 29.5 or something like that, right? And so here you could calculate that angle very quickly just from, 180 minus 59.04, which would give you something like 120, okay, or something close to that. So here, now we want to draw the RVE in this principal stress state. And so we know that if you go 2 theta in Mohr circle, and this rotation, this arrow is going clockwise, that means in quote-unquote real life, you also have to rotate over here to, what is it? What did I say? Clockwise as well. So here, so, and the way I do this here is, look, check this out. I have this line right here, and this represents theta equals 0 right here, like that. Okay. Then I know I'm going to go clockwise. I'm going to rotate this clockwise. So over here, I'm going to draw my horizontal to get to this point right here, to get to sigma 2. To get to this sigma 2 right here, the way I'm going to draw, I have this, here's my theta equals 0. I got to rotate counterclockwise 2 theta P2, which is 29.5 degrees. So that means here, this is 29.05 degrees. Okay? So I draw this first. I draw the horizontal first from theta equals 0. Oh, 29.5. Oops. Okay? 29.5 or 30 degrees right here. And I go, just like I went clockwise in Mohr circle, I'm going clockwise here in my element. And using this line right here, this new line, I'm going to draw a line perpendicular to it. And that's going to be the face of my representative volume element. So that now if I draw this right here is this, okay? Here is this new line right here. Oops. like this. And here was my old horizontal. This is that theta P2 equal to 29.5 degrees. And the state of stress on this face at theta P2 is sigma 2, or minus 8.83 KSI, zero shear stress. So that means I have here 8.83 KSI, going like that. Okay, 8 point. I probably drew that arrow a little too much. I overdid it. I got too excited. Okay, that's 8.83 KSI. And then and then going from there to draw my RVE, I draw out the rest of my representative volume element. Okay, right? And that means I go over here, and I know that going from this side all the way to over here is 180 in Mohr circle. So going from here all the way to this side, right here, all the way to this side is 180 in Mohr circle. So that's 90 degrees in real life. And I went, let's see, to do this, to go like this, I went also clockwise. Yeah? Did I go clockwise too? Yeah, I went clockwise this way. So then if I go clockwise 90 degrees, I get to this face right here. Bam. And that's my sigma 1 face. And this is 2.83 KSI. And that I would have a 2.83 KSI over here by equilibrium. And right here, 8.83 KSI. Okay? Like that. And this would be my principal stress state. Awesome. Yeah, that's my principal stress state. Then I can do, I can do all kinds of stuff. I can go and look at, I never, let me erase this right here. I never drew the complete circle. Okay? You don't have to draw the complete circle because, how many of you carry around a compass just for fun, right? So it's like, what's the point of doing that? So the reality is that like, hey, now for the maximum in-plane shear stress, let's see, can you even see yellow? Let's see, can you see yellow? Can you see that? That doesn't look good. Let's use orange. Let's see, orange right here. So here, we know that the maximum shear stress occurs at the bottom of Mohr circle. So here, somewhere right about here, if I rotate all the way down this way, right here to the very bottom, and I know that this distance is also r, right? It's still the radius, okay? And I just need to find this angle, theta s, the angle to get there, right? And that angle, 2 theta s, right there, that angle right there. And so that angle from what I found before, 2 theta P2 was 29.5, I'm sorry, was 59.4. That makes 2 theta S equal to 90 degrees minus 59.04 degrees, which is 30 point, is that right? 30.96? 30.96 degrees to theta S. And that makes, theta S about 31 divided by 2, which is 15.5 degrees. Okay, theta S, 15.5 degrees. And in this time, I went, instead of going from 0, I went clockwise. I went counterclockwise from 0. Okay, I went counterclockwise from 0. And I know that the value right here of my stress is going to be the radius value. So that's the coordinate of this point is -3, comma 5.83 KSI. Okay, that's the coordinate of that point. And so now if I want to draw, I want to draw my representative volume element here, right? So here again, I go here. I'm over here. I want to draw my I start from theta equals 0, which was over here. And to get to this new point, I had to rotate 2 theta s in Mohr circle counterclockwise, which is 15.5 degrees in real life counterclockwise, meaning I go like this, 15.5 degrees. Okay, 15.5 degrees counterclockwise. And that means I'm on this face of my representative volume element. I'm on that face right there. And so I can go down here now and examine that face right here. Here's that face again. Draw it a little bit bigger so everyone can see it. And here, this angle, which I want to be a little bit more precise. Here is 15.5 degrees for theta s. And on this face, and I can draw the rest of my cube out once with that face right here. Rest of my cube like this right here. And I on that face, I would have a normal stress of -3 KSI. That means here a normal stress of -3, so that's compression of 3 KSI. And then a shear stress of positive 5.83 KSI. And the thing you have to remember is that this always follows a right-hand rule coordinate system, okay, plus and plus like that. So that means that this positive 5.83 is on the plus this face in the plus other direction, or plus x prime face in the plus y prime direction. So a lot of books use like x prime, y prime, or something that sometimes confuses people. But here, this would be right here, this 5.83 KSI. And I could fill in by equilibrium the other parts like this, 5.83 KSI. I have 3 KSI here, like this. And just to make sure that we double check everything, because I am missing one thing here, is that if I go, so if I have this side right here, if I want to look at this side, which is 90 degrees from this surface, okay, 90 degrees from this side, I want to look at this side right here, that is 180 in Mohr circle, which is the top, somewhere over here, okay? And that is also has, this coordinate is -3, -5.83 right here. And that means that I would have over here also this 3 KSI. 3 KSI. And this would be my plane shear stress state. This would be max in plane shear stress. Okay? And this would be my principal stress from before. And the more you do it, the faster you get, and the easier it gets. Okay? All right.